Swayam Prabha. Digital India. Educated India.
Okay, let's get started. Okay, today's class. So we were looking at the Nyquist plot, right? So the Nyquist plot is essentially the plot of the sinusoidal transfer function in the complex plane. Okay, that is, it's a plot of the real part of the sinusoidal transfer function versus the imaginary part, as omega is varied from 0 to infinity. Okay, so that's the Nyquist plot. And we looked at the Nyquist plot of some basic factors yesterday. So we are essentially going to do one example today. Okay, so that's what I am going to do. Just to show you, what is the broad procedure in constructing a Nyquist plot. Okay, some observations that we can make, and then we will start discussing what is called as a Nyquist stability criteria. Okay, so how we are going to use Nyquist plot for control systems. Right, so that's something which we are going to study today. So let me do an example. Okay, we are essentially going to start off with an example in constructing the Nyquist plot. Let us say that we consider a transfer function which is of the form s plus 1 divided by s plus 10. Okay, so essentially the question is, construct its Nyquist plot. Okay, that is the question that we are asking ourselves. Okay, so now how do we start doing it? Essentially first we figure out the sinusoidal transfer function. G of j omega is going to be 1 plus j omega divided by 10 plus j omega, right? So that's what I'm going to get. So of course now what do I do? I just multiply and divide by the conjugate of the denominator factor. So I will get 1 plus j omega multiplying 10 minus j omega, and this denominator will become omega square plus 100, right? So that's what I will get. Okay, so if I now multiply and then simplify this, what am I going to get in the numerator? I will get 10 plus omega square divided by omega square plus 100, and what will be the imaginary part? It will be j times 9 omega divided by omega square plus 100, right? So that's what we will have, correct? Okay, so in terms of magnitude and phase, what are we going to have? So this same thing, if I write the magnitude and phase of the sinusoidal transfer function, the magnitude is going to be anyway the square root of the real part square and some plus imaginary part square, right? So we are going to get 10 plus omega square divided by omega square plus 100 whole square plus 9 omega divided by omega square plus 100 whole square. Okay, so that's the magnitude. And what about the phase? The phase is going to be tan inverse of the imaginary component divided by the real component. So we will get it as tan inverse of 9 omega divided by 10 plus omega square. Am I correct? Right? So these are the various things that we will get, right? So once we process the sinusoidal transfer function, right? And as we are discussing, when you essentially want to plot the Nyquist plot, what you do is that you also create a table and then start plugging or substituting different values of omega that you think are critical, and start calculating the real part, imaginary part, and so on, right? So that you get an idea as to what would happen. Okay, so as these these functions tend to those frequencies, right? So let's look at omega, the real part of g of j omega and the imaginary part of g of j omega. Okay, so let's see what happens at various frequencies, right? So, now if I have omega to be tending to 0, what will happen? What do you think will be the real part and the imaginary part? Please note, the real part is this. What will happen to the real part as omega tends to 0? 0.1, right? So, that is what is going to happen, right. So, as omega tends to 0, the real part is going to be 0.1. What about the imaginary part? It is going to be 0. Now, as omega tends to infinity, what do you think will happen to the real part? It will tend to 1, right. And what will happen to the imaginary part? 0 once again, right. So, if you plot the g of s plane here for this particular transfer function, so this is the real axis, okay. So, this is the imaginary axis and this is the g of s plane. Okay, so let us say we plot this sinusoidal transfer function, right. So, what we are going to get is the following, right. So, let us say this is 0. So, let us say this is 0.1 and let us say this is 1, right. So, as omega tends to 0, the transfer function values tend to, sorry, I think let me scroll down a little bit. Okay, the transfer function values, value, the transfer function tends to 0.1 and as omega tends to infinity, the transfer function tends to 1. Okay, the real part tends to 1, imaginary part is 0. Okay, so now question is that what happens to the locus of the this Nyquist plot for this particular transfer function as omega goes from 0 to infinity. Okay. So, please note that it is going to be the plot of the imaginary part and the real part, right. So, you can see that the real part is always going to be positive for all omega between 0 to infinity, right. So, one can always see that for omega between 0 and infinity, you can immediately see that the real part of g of j omega is always greater than 0. That is something which is pretty obvious, right. And the imaginary part is always going to be, for omega greater than 0, it is also going to be greater than 0, right, and less than infinity. Of course, if I put omega greater than or equal to 0, it is, I have to put it as imaginary part greater than or equal to 0, right. So, please note what am I doing? I am taking omega greater than 0 and less than infinity. So, essentially the imaginary part will be infinitesimally positive. Okay. So, you see that immediately the Nyquist plot is going to lie in the first quadrant. Okay. So, that is something we can immediately see. And as I told you, by and large, if we go and look at it, right. So, sometimes what you can do that you can use intuition, right. So, and by and large when you have these first order factors and when you have such transfer functions, you could try out an equation of a circle, for seeing whether that will be the Nyquist plot, right. So, if I want to have a semicircle whose endpoints are 0.1 and 1, what should be its center? 0.55, right, and what should be its radius? 0.45, right, and it so happens that this I leave it to your homework. Okay. So, if you check this expression 10 plus omega squared divided by omega squared plus 100, which is the real part, minus 0.55 whole square plus the imaginary part square, which is 9 omega divided by omega squared plus 100 the whole square, that is going to be equal to 0.45 square. Okay, you will see that this equation is going to be satisfied, right. So, you will see that the center is somewhere here at 0.55 and we are going to have a semicircle. Okay. So, okay, is this okay? Yeah, it looks like something. Yes, any questions? Okay, so it has the maximum value at 0.55. Okay, so that's what we have, right? So this radius is going to be 0.45. Okay, so that is the what to say Nyquist plot. Okay. So, please do this as homework, like you can double check that this is the case, this is the equation in this scenario. Now, if you want to find out at what omega the phase angle of this particular sinusoidal transfer function is maximum, how would you do that? How would you calculate the phase of this g of j omega at any omega? Graphically, let us say you have the Nyquist plot, right? What do you do? Yeah, so at any omega, what you do is that you draw a vector from the origin to that point, and then calculate what is the angle made by that vector from the positive real axis in the counterclockwise direction. That is taken to be positive convention, right? So as you said, if I want to figure out the maximum angle, I need to draw the tangent, right? So from the origin, I see which point, at which point essentially I can get a tangent to the semicircle, right? So essentially, let us say this is my tangent, right? So this is the omega, what I call as omega m is the frequency at which I get the maximum phase phi m, okay. So phi m is the maximum phase of g of j omega, right. So the Nyquist plot helps us with all these things, and we will see why this is important, okay. I have chosen this example with a motivation, right. All the examples I am choosing finally lead to some consequence, okay. We will see, okay, and maybe in the next few classes we will see why this is going to be important, okay. Why did I choose this particular example, and why am I talking about the maximum phase contribution, right, or phase angle of this particular transfer function. So you see that phi m is the maximum phase of g of j omega, okay. Omega m is the corresponding frequency, okay. Now how can I calculate phi m? Is there a way to calculate phi m? Even using geometry? Phi m is that angle, right? I am sure all of us agree, right? You just using geometry, can you calculate phi m, right?
Equate the tangent at a point.
Phi m is this angle, right? So see, let us say, of course, if I draw this, you will get the answer, right? Let us say I draw a line segment from this point to the center of the circle, semicircle, right? What is the length of this line segment? The radius. What can you say about the angle made by the tangent and the radius? 90. Now do you have the answer? What is sin phi m? This is 0.45. Then, so we notice that sin phi m is going to be 0.45 divided by 0.55. Can you calculate phi m and tell me? So this is 54.9, okay. So essentially you can see that this is the maximum phase that is contributed by this particular transfer function, okay. And by and large, if this phase angle is positive, that means that there is a phase lead, okay. And if the phase angle is negative, that means there is a phase lag, okay. So in general, okay, so this is just an aside, okay. So if phase is greater than 0, okay, we call it as a positive phase, right. So, positive phase angle, okay. So, it is also called as phase lead, okay. So, essentially, okay, or lead factor, okay. So, but if you have a negative phase angle, okay, phase is greater than less than 0, okay, that essentially denotes a negative phase angle, that is what is called as a phase lag, okay. So, you see that this particular factor adds positive phase, right. So, essentially it provides a phase lead, and the maximum phase lead that it can provide is around 55 degrees, okay. We will see why this becomes important, okay, as we go later, okay. Please remember this, okay. So, we will use it later on, okay. Now, how do you find omega m? Of course, there are, you know the equation for the phase angle, okay, and then like you plug it in and then calculate omega m, right. You know tan phi m, that is going to be 9 omega m divided by 10 plus omega m square, right, is it not, right. So, for finding omega m, you know that tan phi m is going to be equal to 9 omega m divided by 10 plus omega m square, okay. So, if you solve this, you will get omega m to be equal to 3.162, okay, of course radians per second, okay. So, you please do this as homework once again, okay. So, this is also a homework problem, okay. So, that is something which I will do, right, please do this, okay. And one more thing which we are going to do is that I am going to leave you with another homework problem. Plot the Bode diagram of this G of s, which is essentially we took it as s plus 1 divided by s plus 10, okay. So, the same transfer function, plot its Bode diagram, okay. Please do this as homework, okay. Please do this and compare, right. I think we have already discussed Bode diagrams in detail, we have done an example in class also, but let me get you started. So, how do you plot the Bode diagram? Of course, you need to divide into particular factors, right, okay. So, what do we do? If G of s is going to be this, I can rewrite this as, I need to rewrite in the standard form, right. I can pull 10 out from the denominator. So, I am just going to get 0.1 s plus 1 divided by s by 10 plus 1, correct. Do you agree? Okay. So, it has 3 factors. So, this means that it has a 0.1 scalar, and then you have a s plus 1, and there is an s by 10 plus 1, okay. 3 factors are there. So, you plot the Bode diagram for all the 3 individual factors and then add them, right, the magnitude plot and the phase plot, okay. So, what are the corner frequencies of these factors? If you consider s plus 1, what is the corner frequency? Corner frequency 1, right. And what about the corner frequency of s by 10 plus 1? 0.1 or 10? 10, right, because it is Ts plus 1, right. So, and corner frequency is 1 by T, okay. Capital T is the coefficient of S. So, here is 1 by 10, then you take the reciprocal. So, the corner frequency is going to be 10. So, now can you relate 3.162 to 10 and 1? No. Of course, I am just playing with numbers, but then you will see that it translates into generality for such factors, right. So, I have chosen these numbers for due to a particular motivation, which will become clear as I told you. So, how can you relate 1 and 10 to 3.162? No. square root of essentially 10 and 1, right. So, when you use a logarithmic scale, where is 3.162 going to be? So, let us say you use a logarithmic scale, right, okay, for omega. So, you have 10 and 1, where is it going to be? Midpoint, right. So, exactly why? Because if you want to essentially do 1 times 10, right. So, you take the log to the base 10. So, first of all you have log of square root is 1 by 2 of log, correct? Do you agree? And then log of a times b is going to be log of a times, sorry, log of a plus log of b. So, this is going to be, of course, we are doing log to the base 10. So, what are we going to get? We are going to get the midpoint, right. So, when we do this one in the logarithmic scale. So, you see that for this particular factor, the maximum phase is going to be at the, of course, what do you call as, let us say I give you two numbers, you take the product and you take the square root of that, what do you call that as? Arithmetic mean? Geometric mean, is it? Or arithmetic mean or something else? Geometric mean, right. So, you see that the phase, that is frequency at which you get the maximum, what to say, phase contribution from this is going to be at the geometric mean of the two corner frequencies, right, in this particular case, right. So, that is what we are getting, and this particular factor, particular transfer function, we will generalize and we will use it in control design, okay. So, that is why I am doing this in this example in so much of detail, okay. So, please go back, like I cannot be, what to say, essentially more, I cannot emphasize this more. Please go back and draw the Bode plot, because you will see that you will need it in control design, okay, using frequency response. Kindly do that, okay. Yeah. Yes, any questions? Okay, so please go back and plot the Bode diagram and then compare it with the Nyquist plot, okay. So, that is what I want you to do as homework, right, okay. So, so we see that what we have done is we have looked at the frequency response, we have looked at what to say, the Bode diagram and the Nyquist plot, which are two essentially methods to visualize the frequency response of transfer functions, okay. There is a third plot which is called as a Nichols plot, okay, which I leave it to your homework, okay. So, we are not going to use that in this course, so but if you are interested you can go back and look at that, okay. So, once again it is just a visual representation of the sinusoidal transfer function, okay, that is about it.
So, this geometric mean result is true for all s plus a by s plus
all s plus a divided by? Okay. So, factors of this form will give you a, that is what I am saying, like I am not going to generalize here, it depends on the value of a and b, okay, we will come there. So, please wait for a few more classes, okay. So, that is why I am being careful to not to extrapolate right now, okay, please hold on, okay. That is a good question, okay. He is asking, okay, if you take a transfer function of the form s plus a divided by s plus b, right, is this result going to hold in general? Partly yes, partly no, okay, depends on the value of a and b, okay, we will see, okay, as we go along, fine, yeah. Oh yes, yes, thank you. Yeah, sorry about that. Now let me erase this. Yeah, yeah, this should be 1 divided by s by 10 plus 1. You are right. Thank you. Okay. Yeah, sure. Okay. So that's what you have. But then, like, you can also make some general observations, right? What are the values of n and m? It's essentially 1 and 1. So, is this a minimum phase transfer function? It is, right? See, because typically, see, by the way, I think I should highlight this point. There are two groups or two, what to say, ways in which people look at a minimum phase transfer function, okay? or minimum phase systems, right, some people associate it only with zeros, okay, because they implicitly they assume a stable system to begin with. See, if you take any transfer function which is of the form n of s by d of s, right, how did we define a minimum phase transfer function? One whose zeros are in the left of complex plane. You know, it was implicitly assumed that the poles are in the left of complex plane, because when we talk about frequency response, you recall that we are talking about stable systems, then only frequency response makes sense, right. So, implicitly we are assuming all the poles to be in the left of complex plane. Another school of thought essentially tells that, you know, minimum transfer function is one where all its zeros and poles are in the left of complex plane, okay. So, I just wanted to highlight that difference to you, these this alternative notion, okay, or definition to you. The reason why I wrote the definition as what to say, minimum transfer function being one where all its zeros are in the left of complex plane was that because I implicitly assume that all the poles are already in the left of complex plane. Is it clear? Okay, so that is a subtle difference I wanted to highlight. Okay, so this is a minimum phase transfer function. If you recall a minimum phase transfer function, what is the what to say, in general the slope of the high frequency asymptote? Did you recall our discussion? Slope of the magnitude curve. See, if this is of order m and this is of order n, what is the slope of the high frequency asymptote? Minus 20 times n minus m decibels per decade, right. Is that satisfied here? Yes, right. Why? Because s plus 1 will contribute plus 20 decibels per decade, 1 divided by s by 10 plus 1 will contribute minus 20 decibels per decade. What is going to happen? Both are just going to cancel out each other, right. That is what is going to happen. That is point number 1. And what can you say about its phase as omega tends to infinity? What is going to happen to for a minimum phase transfer function? You remember, the phase tends to minus 90 times n minus m, right. So, these are the results as omega tends to infinity. The magnitude tends to this one, the phase tends to this for a minimum phase system, right. So, what is going to be the value here? 0. And does it tend to 0? It does, right, because s plus 1 will give you a phase contribution of plus 90, 1 by s by 10 plus 1 will give you a phase contribution as minus 90 as omega tends to infinity. So, the sum is going to be 0. And can you observe it from the Nyquist plot? You can, right, because what is the what to say, transfer function, where is the transfer function as omega tends to 0? 1, not 0.1, 1. See, as omega tends to what to say, infinity is this. Where is it at omega tending to infinity? It is at 1, right. If the transfer function is at 1, what is the angle made by that? See, how do you get the angle? You draw the vector from the origin to that point, right. So, you are going to have a vector which is aligned along the positive real axis. So, what is the angle? 0 degrees, right. So, I am just what to say, we are just double checking the results. Is it clear? Okay. So, you can see that the results that we discussed hold true. Okay.